Good morning, everyone. I just want to thank all of you for being here. Thank you, Jan, for allowing me this space to present. In this talk, I will argue that the long-term tectonic loading plays an important role in the occurrence of intraplate earthquakes. While intraplate earthquakes are not fully understood, some scientists theorize that as the tectonic loading is close to zero deep into the continent, it has to be negligible in the activation of intraplate earthquakes. It means that some concepts, such as the recurrence time and the fault slip rate, do not apply on these areas. And in this talk, I will take you to the Bulnay fault system, where we actually could see how earthquakes do repeat in time in consistency with the fault slip rate. But let's first introduce the Bulnay fault system and why it is so famous. Well, the Bulnay fault is an east-west left lateral strike slip fault system located on the western, on the western side of Mongolia, northwestern side, and despite of being a slow-moving fault, it sustained the largest intracontinental earthquake sequence ever recorded. What do we know about this sequence? So in 1905, there was a magnitude 8 earthquake occurring along the Sexer Lake fault here, and 14 days later, another magnitude 8 occurred along the Bulnay fault just here. And these earthquakes together rupture about 676 kilometers. And at the bottom here, you have a coseismic slip distribution measured all along the fault. And it shows an average slip of about 6.5 meters for the Bulnay fault and 2.5 meters for the Sexer Lake rupture. So the first question is, are those orphan earthquakes? Do they repeat in time? What do we know about the seismic history? Well, paleoseismic investigations shows that indeed those earthquakes repeat in time. In 2015, Magali and others excavated the one trench here in the Bulnay fault. This is the interpretation of the trench, and here I highlight in red dashed line the earthquake horizon associated with the 1905 earthquake, and they identified as well 2 additional paleoearthquakes. They gave us a first approach, or a first recurrence interval of about 2.7 to 4,000 years for this fault. And in the recent years, Benjelon and others excavated a trench along the Sexer Lake fault, across the Sexer Lake fault, and they identified as well some deformation indicators for the 1905 and additionally 2 paleoearthquakes, with a recurrence interval of about 8.5 thousand years. So we have a first estimation of the recurrence interval. However, paleoseismic trenches has some important limitations here. On one hand, you will find a permafrost layer in the very few centimeters below the ground, and this poses some challenges when you want to excavate a trench, as well as it might cause cryoturbation. And on the other hand, the earthquake-related deformation can be widely constrained in time due to the lack of datable material. So what we propose here to overcome this issue is to use lakes as earthquake archives. Why lakes? Well, thanks to the water column here, lakes are isolated systems from the external perturbations, climatic perturbations, so you don't have to deal with the permafrost layer. And additionally, due to the continuous sedimentation, you have a quite high resolution in time along these systems. So, and this is interesting because those systems are quite sensitive to earthquake shaking. So when an earthquake occurs in the nearby areas, it will destabilize the slope. It will eventually create a turbidity current that will bring all the material from the borders of the lake down to the depot center. And if we take a look carefully in the depot center, what we can see is that first, the background sedimentation, here represented by the white layer, and then some, say, allogenous material, or called terrigenous material, coming from the borders of the lake. those are arranged in a certain way, which is called normal radiation, and normally is sealed by a clay cap at the very top. So it turns out that along the Bulnay fault, we have quite good numbers of lakes. Here we have the main lake system on the eastern side, the Kjargas Lake, and some of them are, well, most of them are distributed in the middle and the eastern side of the fault, as you can see here. Well, at this stage, we target 7 lakes based on the spatial distribution around the fault. And then we went to the field. Once on the lake, we control the bathymetry using a sonar, and once reaching the depot center, we use a gravity core. You can see here, Jan is holding the gravity core, and we just collect one short core here from one of the lakes. And we end up with about 20 meters of sediment cores from 7 different lakes. But as you know, some of us can have logistic problems and fieldwork problems, where this time we have both of them. But the most significant was that those courses stayed too much time in Mongolia, so they got frozen, and we lost half of them, more or less. So they got damaged. However, fortunately for us, some of them survived. As you can see here, we opened them all, and I was quite glad to see that they were still alive, and also to see how well preserved was the stratigraphy in those cores. But I had new concerns because I couldn't see any signatures of paleoturbidite directly by site. So because of this, we use a combination of different high resolution and of physical analysis and chemical analysis in order to look more carefully into these cores. So once we have done all of these measurements, the question is, how do we recognize signatures of paleoearthquakes? Now let me take you lake by lake to answer the question. So we end up with 3 out of 7 lakes. The first one is here, the Oigon Lake, located 5 kilometers south of the fault. And as you can see here in the satellite imagery, we are in a highly evaporatic environment. Those are salty deposits. And in the white star represent the position in which we collect these cores. Here we have a short one and a longer one of about 1 meter and 20 centimeters. On the side, I represent the organic material that we collect from the cores in order to have a constraining time of these cores. And I have some chemical logs that were essential to recognize these paleoevents. So why I show you particularly titanium, zirconium, and clay? Well, those are because these elements are quite related to heterogeneous material. And if you see carefully, at a certain depth, there is a systematic increase of the relative, a systematic increase of these elements that can be interpreted as an additional input of the heterogeneous material into the depot center. So we target those points. We took some samples to do thin sections, and we arrived to see our paleoturbidites. More precisely talking, I was dealing with microturbidites right here. So here, this is a photo from a microscope, electron microscope, and at the bottom, this is a geochemical cartography for the same area. In yellow and red colors, this is represented the input of silica and iron into the system, which is related to our heterogeneous material that highly contrasts with the background sedimentation of the lake, represented in green and blue color. So the next step was to build a Bayesian age model in order to know when those events occur in time. So here you have each of the gray curves represent the calibrated age C14 samples here, and each of the orange probability density functions represent the age of the paleo events. So in this particular core, we we have a sedimentary record of about 2.5 thousand years. We identified 4 deposits, and as you can see in red. And one important thing here is that the very top of the core didn't match with the present day, according to the age model. So it falls indeed more or less in about 1,500 years AD. And this is telling me that this particular lake system is dealing with a reservoir age of about 500 years, more or less. If we account for this reservoir age, this particular signature in the upper part might be related to the 1905 earthquake. Let's go to the second lake. Here is located on 25 kilometers south of the fault. Again, we see some signatures of relative increase of these elements, but in this core particularly, we target the upper part that we see a slightly bulge or positive anomaly of these elements. We target this place, and voila, we found some evidence of our 1905 paleoturbidite. So those were quite good news, because now we were certainly sure that those systems, those lake systems, are recording earthquakes. Well, how we were so sure that this was 1905? This event perfectly is consistent with the age model, and additionally, the very top part of the core perfectly match the present date. So this particular lake doesn't have any reservoir age. In this lake, we have a record over the last 6,000 years, and we identified basically 3 paleo events. Then going to the third one, the third lake is divided into 2 subsystems, on the north and on the south. This particular core was highly damaged at the upper part, so well, we couldn't find any trace of 1905, but still we kind of identified some anomalies. And I was particularly interested in this transition from sandy deposits up to salty silt to clay deposits. So I wanted to know when those events occur in time, so I built a model. And despite we don't have any signature here of the 1905 earthquake, this particular core was the longest one in terms of time of sediment record. It is spanning about 10,000 years over the past, and we identified here 3 deposits with a reservoir age again of about 600 years. Finally, going to the south of the lake system, this was good because in this particular lake, again, we see a positive signature of titanium. And additionally, we found the first paleoturbidite recognizable by sight, with a 1 centimeter thick, more or less. We did some geochemical cartography to identify them. And this particular event, again, this particular lake, present a reservoir age of about 600 years, in consistency of what is observed in the north. If we account for this time shift, this particular event that we observed at the top indeed represents the 1905. And we have a sediment record over the last 3.5 thousand years with 3 events recognized here. So far, I have shown you different evidence of paleoturbidites. Now I would like to summarize everything, to zoom out and summarize everything, and in order to draw as well some conclusions. But the first conclusion seems that the Bulnay fault system is more active than previously thought. Here in this plot, you have distance along the fault, and you have the calendar date on the vertical. And here I represent all of the probability density functions associated to the age of the paleo events. I additionally represent with these vertical bars the time interval observed in the trench done by Magali in Bulnay, and the yellow bar represents the time interval for the paleo earthquake observed in Texas Lake Fault. And as a first look, you can see that most of them those are quite, let's say, contemporaneous in time, which is what I want to highlight with the red horizontal bars. So, but let's take a look. Let's start with this particular event. Well, this event corresponds to the transition between the sandy deposits and all the silty material. And it seems to overlap in time very well with a rupture observed here along the Bulnay fault, in the Sexer Lake and along the Bulnay fault system. We believe that this was a major earthquake, likely similar to the 1905 that involved both faults, and it was likely related to the creation of the Singing the Light Lake that will eventually allow for the deposition of the sedimentary deposits in the lake, silty deposits. So this was a major event that might have induced, let's say, full relaxation of the stress field, so that it would take about 4.4 thousand years to build up again stress and before the next earthquake to occur. This event apparently was observed as well by the trench done by Magali, and it seems to have ruptured just along the Bulnay fault, but it doesn't stop over there. 1.3 thousand years later, another event occurred along the Bulnay fault, and this one particularly again was observed in all the three lakes. Finally, 1.8 thousand years, again, we have a huge sequence of earthquakes occurring here in 1905. So we can say something interesting about this fault system, and is that it seems to have periods of independent rupture behavior involving only Bulnay fault, but it seems that there are periods in which the fault seems to interact, allowing for a synchronized rupture behavior. And those synchronized rupture behaviors seems to be followed by long lull interseismic periods, as you can see here. So we could say that at the present day, we are likely at the early stage of a multi-millennial long lull period. So that's one of the main conclusions. And as this is an ongoing work, there is still some ongoing measurements of session and lead to calibrate the reservoir age, and some additional intersections to hunt some paleoturbidites in this particular lake. Thank you very much.